Hi, hello everyone. Welcome back to my YouTube channel. This is Soumya. This video is on two more concept on the mechanism of light phase. Yes, in this video we are going to discuss the concept that is Emerson enhancement effect, and the second concept is molecular configuration and orientation of supramolecular complexes, or you can say domains or assemblies. Give a short introduction or quick recall so that you can understand this video better. So in the previous video we were talking about the mechanism of light phase, and also have told that there are about seven stages are there, or 7 steps are there in the light phase. So this is what is this light phase? Light phase is a photochemical process, and it occurs in the thylakoid membrane. This is very important. It occurs in a thylakoid membrane. And in the previous video I also talked about the photolysis of water. Photo means light, lysis means breakdown of water. And also we studied about the Hill's reaction. Rofin Hills said that water is the source for the release of oxygen in photosynthesis. So okay, we have studied all these things in detail in the previous video. If you didn't watch that video, you can watch that video. If you are interested, I have given the link in the description box, and thank you. So now video we are going to talk about this one, that is second one, Emerson enhancement effect, and third one, molecular configuration and orientation of supramolecular complexes, domains and assemblies. Okay, now let's begin with the first one, that is Emerson enhancement effect, and this concept is important here. What is this Emerson enhancement effect? Emerson is a scientist. Okay, he did an experiment on quantum yield. Okay, what is that quantum yield? We will learn about that. We are talking about the photosynthesis, right? Now there is a question that how we are going to measure that how much photosynthesis have been occurred in a plant or a leaf. So to measure that, there is a concept called as quantum yield. So one measure of photosynthetic yield is quantum yield. It is a unit of measure of rate of photosynthesis. It is a unit of measure of rate of photosynthesis, and he did experiment in a chlorella plant. Okay, what is this quantum yield then? So before that we will learn one more term, that is quantum requirement. The number of photons or quanta. Number of photons means, I have already mentioned this. Photon means it is an energy pocket, or you can say quanta. This energy comes from where? From sunlight, or you can say radiant energy. So the number of photons or quanta required by a plant or by a leaf to release one molecule of oxygen during photosynthesis, that is called as quantum requirement. How many number of photons are required to release one molecule of oxygen during the photosynthesis? That is called as quantum requirement. Then what is quantum yield then? So we will learn this now. Quantum yield, this is the another name for the quantum yield is photochemical efficiency, and the symbol for this quantum yield is this one. Okay, pi. Okay, so now look at the definition here. The quantum yield for the light reaction, because we are talking about the light phase, right? The quantum yield for the light phase or light reaction or light dependent reaction in photosynthesis is the number of oxygen molecules evolved by one quantum of light, means photon, in the process. Here this definition says that during the photosynthesis, the number of molecules of oxygen evolved, means the number of oxygen released by one quantum of light, that is called as quantum yield. And there is a formula for that. The formula is here, quantum yield or quantum efficiency. Here the formula is that number of oxygen molecules released divided by number of photons observed. Means number of photons are observed means from during photosynthesis. Think this is the plant. Okay, so this is the leaf. So how many this is the sun, and how many number of photons observed by this leaf or a plant to release one molecule of oxygen, that is actually called as quantum efficiency. Okay, so how many number of photons are observed to release one molecule of oxygen, that actually gives the quantum yield or the quantum efficiency. Next, moving on to the next points here. Emerson and Arnold carried out quantum yield experiment in monochromatic light. Now we will learn about how they have found out this. We will learn about the experiment conducted by Emerson and Arnold to carry out the quantum yield. They did the experiment by using a monochromatic light. Okay, mono means a single. So single light, monochromatic light. In the first set of experiment, what they have did, they used the red light of longer wavelength. They use the red light of longer wavelength, means the wavelength is about 680 nanometer or above 680 nanometer. For example, here they have taken 700 nanometer. Okay, when they observed, the photosynthesis yield decreased. That is actually called as red drop phenomenon. This point, red drop phenomenon, is important here. So in first set of experiment, what they have did, they supplied the red light of longer wavelength, which is above 680 nanometer, to the plant to conduct the process of photosynthesis. But when we observe, the photosynthesis yield is decreased. There is no enhancement in the photosynthesis yield, that is quantum yield. So they moved on to the next set of experiment. In this set of experiment, what they have did, they again use the red light, but now this time they use the shorter wavelength. Okay, that is about 680 nanometer or below 680 nanometer. Okay, so they took around 650 nanometer red light, which is of a shorter wavelength. That time they observed the photosynthetic yield. That time also photosynthetic yield is decreased. So there is a drop in the photosynthetic yield, that is quantum yield. There is a drop in the quantum yield, that is actually called as red drop phenomenon. Okay, means here red color, which is a longer wavelength or it may be a shorter wavelength, there is a decrease in the quantum yield when they did the experiment using a monochromatic light. Okay, mono means single chromatic light. So in these two experiment, in these two set, they didn't get the expected yield. So what they have did in the third set of experiment, they combined red light of longer wavelength with the red light of shorter wavelength simultaneously. Simultaneously means at a time. They given the red light of longer wavelength and red light of shorter wavelength, they given at the same time, so that when they given at a simultaneously means at the same time, then they observed that they got to know that there is an increase in the efficiency, there is an increase in the quantum efficiency into a greater level. Okay, by this experiment they got to know that, or they proposed that the photosynthesis involves two systems. Okay, that is, one of the system requires red light of longer wavelength and second system requires a red light of shorter wavelength. Okay, now next point, and this photosynthesis yield, okay, will be normal and productive only when two systems are functionally cooperatively and synergetically. So if you want to see the photosynthesis yield or quantum efficiency, that is only going to happen normally and productively when the two systems, that is red light of longer wavelength and red light of shorter wavelength, should be given simultaneously or cooperatively or synergetically. Then only you can see the yield. Okay, and what are those longer and shorter wavelength? These two systems are called as photosystem 1 and photosystem 2. Okay, so these two systems are photosystem 1, photosystem 2. Here photosystem 1 requires red light of longer wavelength and photosystem 2 requires red light of shorter wavelength. See, don't neglect any of the points which I am explaining here, because all these points are important to learn the another concept. So be always connected with the content. Don't miss out a single point. If you miss out a single point, you are not going to understand the next concept. And also connections, how we are going to connect your knowledge from previous knowledge to the new knowledge, how we are going to add the knowledge so that you are going to understand in a better way. Okay, so photosystem 1, it has the red light of longer wavelength, and photosystem 2 have the red light of shorter wavelength. And this photosystem 1 and 2, important here, photosystem 1 and 2 together drive non-cyclic electron transport, which releases oxygen, okay, which gives the quantum yield. Okay, but the cyclic electron transport, that is CET, involves only one photosystem. That's why it doesn't releases oxygen, means there is no quantum yield. That's why this experiment itself, they have proved that it requires two systems, that is PS1 and PS2. PS1 with the longer wavelength, PS2 with the shorter wavelength. Okay, that's about the PS1 and PS2. So what is the conclusion for this Emerson enhancement effect here? Emerson effect says that there is the increase in the rate of photosynthesis Okay, there is an increase in the rate of photosynthesis when light of two different wavelengths are provided together. So this experiment is the evident that the presence of two systems, that is photosystem 1 and photosystem 2.
Okay, now we will move on to the second concept, that is molecular configuration and orientation of supramolecular complexes.
So now we have to learn about electron transport now. So what is this electron transport? As in the name indicates, it is very easy to understand. There is a transport of electrons, but how it is going to happen and why it is going to happen. So that we have to learn, right? So the transfer of electrons from water to NADP plus is called electron transport. Okay, as you can see in the diagram, the transfer of electrons from water to NADP plus is called as electron transport. Okay, but however, electrons cannot be transported directly from water to the NADP plus because of mainly two factors. That is, the first one, because of physical barrier. Second one, there is a reduction potential gap between water and NADP plus. Okay, now we learn these two. What are these two factors? That is physical barrier and reduction potential gap between water and NADP plus. Okay. Before that, for make you to understand, I will just draw a rough diagram. So I'm hoping that this diagram will help you to understand the concept better. So I already said before that this light phase or light reaction is going to take place in thylakoid membrane. So I'm just drawing the thylakoid membrane here. And also by emerson effect, so thylakoid membrane I am drawing here. So if it is a thylakoid membrane and this side is a lumen, okay, and this is a thylakoid membrane, this is a thylakoid membrane, and this is stroma. Okay, this is stroma. So this, right, this is the chloroplast, and we have the stroma, this is the stroma here. Okay, and these are the thylakoid membranes or and our granule, you can say. This is the thylakoid membrane. So if you take this, so if you we are focusing here, okay, we are focusing like this. This one only I am drawing here. Okay, this one only I am by enlarging it. So I am just enlarging this one and drawing this one here. Okay, and this stroma here, this is the stroma side, this is thylakoid membrane, and this is the lumen here. And we can see here, and also by emerson effect, emerson enhancement effect, we got to know that there are two systems, that is photosystem 1 and photosystem 2, right? So there is a photosystem 1 and there is a photosystem 2. Okay, so this is photosystem 2 and photosystem 1. Okay, and in lumen we have water here. Okay, we have water here, and here water, here what I said, photolysis of water, water has to transfer the electron to the NADP plus, right? So here what happens, step by step, electron carrier 1, it transfers the electron and to the 2, and then to 3, and then it transfers the electrons to the 4th one, and then it transfers to the 5th one, and this one transferred to the 6th one, and this one is transferred to the 7th one, and it carries to the 8th one, and it carries to the 9th one, and it carries to the 10th one, and it carries to the 11th one, and it is now then reaching out and giving it to the NADPH. Okay, so these are all what, there is a electrons are going to carried by these electrons carriers. Okay, and this complex, okay, don't worry about this complex, I will explain this complex as well, but for time being just remember this is the cytochrome B6F. Okay, so just imagine this diagram, this is the thylakoid membrane, and this side is lumen side, and this side is stroma. In the lumen you are going to find out the water here. So this water is, there is a photolysis of water, and the electrons are transferring through the electron carriers to the NADP plus. Okay, now so the transfer of electrons from water to the NADP plus is called as electron transfer. The transfer of electrons from water to the NADP plus is called as electron transport. Next point, however, electrons cannot be transported directly from water to NADP plus because of two factors, that is physical barrier. Second one, reduction potential gap between water and NADP plus. So you can see here there is a physical barrier here. So because water is in the lumen, Okay, you can see here water is in the lumen and NADP plus is in the stroma, right? So by diagram itself you guys can understand here that so water is in the lumen and plus is in the stroma. So that electrons should move from lumen to the stroma. So then it requires electron carriers, right? This is actually creates a physical barrier. The electron donor, that is water, is in the thylakoid lumen and the electron acceptor NADP plus is in the stroma. Thus, there is a physical barrier in the form of thylakoid membrane between water and NADP plus. Hence, electron carriers are required to transfer the electrons from water to the NADP plus to avoid this physical barrier. Okay, next, second one, reduction potential gap between water and NADP plus. Here what happens, the electrons of water are at low potential or you can say at the lower energy level, and electrons of NADP plus are higher potential or higher energy level. So this energy gap is between these two, or this energy gap is filled up by a radiant energy, that is sunlight energy. So you can see here it is in the lower energy level, this NADP plus is in the higher energy level, and there is a difference in the energy levels, and this energy difference gap is filled by a radiant energy. The radiant energy is nothing but here sunlight. The radiant energy source is sunlight here, right? This radiant energy, what this radiant energy will do? This radiant energy excites these electrons of water from the lower energy level to higher energy level of the NADP plus, for efficient transfer of these energies, that is electrons, electron carriers are required, and these electron carriers are found on the thylakoid membrane. So these electron carriers are found on the thylakoid membrane. As you can see in the diagram, you can clearly know this is the thylakoid membrane and electron carriers are in the thylakoid membrane, right? And some of these electron carriers come together to organize into a complex on the thylakoid membrane. These electron carriers attach to protein complex on the thylakoid membrane, and these protein complexes thus contains the electron carriers involved in electron transport, and these are called as electron transport complexes or assemblies or domains. So that's why these are called as electron transport carriers or electron transport domains or complexes, that is photosystem 1 and 2 and cytochrome B6F. Transfer of electrons from water in the lumen to NADP plus in the stroma via electron transport complexes on the thylakoid membrane is called as electron transport. So, at the beginning of this video, I have given the definition, the electron transport in a simple manner. Okay, what is that simple definition? The transfer of electrons from water to NADP plus is called electron transport. If I have to give a definite and more specific definition, the specific definition is here: the transfer of electrons from water in the lumen to NADP plus in the stroma via electron transport complexes on the thylakoid membrane is called as electron transport. Okay, so the transfer of electrons from water in the lumen to NADP plus in the stroma via electron transport complexes on the thylakoid membrane is called as electron transport. Next, and the supramolecular complexes found on the thylakoid membrane includes photosystem 2 and cytochrome B6F complexes and photosystem 1, and there is a light harvesting complexes that is called as photosystem 2 and photosystem 1, that is LHC2 and LHC1. These each photosystems, that is LHC2 and LHC1, contains two basic components. Again, these two systems consist of two basic components, that is reaction center and then second one antenna complexes. Important, these two are important. First one, reaction center. What is this reaction center? It contains a pair of special chlorophyll molecules in the core of the photosystems. So if you think this is the photosystem, these two are the photosystems, right? In the core of these photosystems too, it contains a pair of special chlorophyll molecules. Okay, that actually forms the reaction center. Okay, and second one, antenna complexes. What are these antenna complexes? Antenna complexes nothing but these contain a antenna pigments. Okay, these pigments absorbs radiant energy and transfer the excited energy to the reaction center found in the core of the photosystem by radiant energy transport. And again, the antenna complexes are again of two types. Okay, first one, internal antenna, which is found in the core of the photosystem. Second one, external antenna, that is LHC, that is light harvesting system. Okay, so that's about this video. In the next video we will discuss about these molecular configurations or supramolecular complexes in detail. Okay, and also if possible we will start with the mechanism of non-cyclic electron transport system, and mechanism of NET is important for the examination. Okay, and hoping this video will help you all, and it's my pleasure to teach you all. Thanks for watching.